Today we are going to talk about how to interpret mass spectra for the AP Chemistry exam. Mass spectroscopy is an analytical technique that allows us to measure the masses of atoms and molecules. How is this possible? Well, we use a machine called a mass spectrometer, as shown in the diagram on the right. The process occurs in four major steps. So the first one is ionization. Here the sample is vaporized and electrons are removed from the particles to give it a positive charge. This is important because magnetic field has no effect on neutral particles. Then the second step is acceleration. The charged particles in this step are given the same kinetic energy so that the only factor affecting its deflection is the mass. The third step would be deflection. Using powerful electromagnets, the magnetic field produced is able to sort the ions into their respective masses. Remember that the heavier the ion, the smaller the deflection. And finally, detection. The sorted ions will hit the detector at different points depending on their mass, and the number of hits can also be recorded for each one. Remember that lighter ions are deflected more than heavier ions. And because of this, different isotopes can be sorted and detected. For example, naturally occurring carbon has many isotopes. So when you put the natural occurring carbon inside the spectrometer, carbon 12, carbon 13, carbon 14, and all the other carbon isotopes will hit the detector at different points. So now we can sort it out. And the good thing here is that the number of detections can also be measured. The number of hits for each mass can be measured, and in so doing, the relative abundance for each mass can be determined. For every 10,000 carbon atoms that goes through, about 9,890 carbon 12 and 110 carbon 13 will be detected. So we can actually find the relative abundance. So, in AP Chemistry, this is your typical mass spectrum for our organic molecule. But in AP Chemistry, we are going to use a very simple one, wherein you have only the atomic mass units on the x-axis instead of the mass to charge ratio, and we have percent abundance on the y-axis. And we will be only concentrating on monoatomic ions. So here, as you could see for the mass spectrum for copper, the x-axis, atomic mass units, you will find the number of peaks. The number of peaks correspond to the number of isotopes. In this case, there are two peaks, the first peak, the second peak. So indicate that there are two major isotopes for copper, and we can also name it. The mass under each peak is the mass number of that isotope. For example, we have copper 63 and copper 65. On the y-axis, this could be percent abundance, relative abundance, or relative intensity. So this is a percentage. The percentage of hits for each isotope from the total hits for that element. So for all the total hits, 70% of the hits come from copper 63 and 30% of the total hits come from copper 65. If the numbers do not add up to 100, then you have to recalculate the percentages. Now, for example, here, we can determine the average atomic mass of copper from the mass spectrum. So we list down the two isotopes, copper 63, which has an atomic mass of 63 from the mass spectrum. The abundance is 70%, as we can read from the y-axis. And then for the other isotope, copper 65, we get 65 from the x-axis, and then 30% from the y-axis. Remember that the atomic mass here is estimated. Normally, it's not just 63. It's more precise than this, but we can estimate the atomic mass from the mass number. Now we multiply the atomic mass and the mass number so that we get this 44 and 20, and then we add them up, and as you add up, you get 64. The 64 is actually the value, is what we call the average atomic mass, and this is the value found in the periodic table for naturally occurring copper, which is consistent with what is written in the periodic table. So the periodic table, in essence, gives you the average atomic mass. It does not give you the mass numbers, but you will be able to know which one is the more abundant. In this case, copper 63 is the more abundant, and that's why the average, which is 63.546, is closer to copper 63 than 65. So, the mass spectra can actually provide the following information. The identity of the element can be determined, and consequently, the number of protons. The number of the most common isotopes for that element can also be determined, the mass number for each isotope, and consequently, the number of neutrons, and the percentage abundance for each isotope. All these information are provided by the mass spectra. Now, let's look at some of the sample questions that normally come out in AP. For example, you're given the mass spectrum of an element X, so that we don't know what this element is. The question is, the mass spectrum represented above is most consistent in which element in the periodic table? How do we do that? Then second, based on the spectrum of a pure element represented, you're asked for the average atomic mass. So the first one was the identity of the element. The second one is the average atomic mass. And specifically, it's asking for the isotope with the mass number 88, how many protons and neutrons are there. So let's see. So we found out that the most abundant is 88. And you have all these other isotopes which are actually smaller in percent abundance. And so when you take the average of this, we know that it's going to be close to 88, but a little less than 88. And that brings us to strontium, because it has an atomic mass of 87.62, which is perfect. It can't be Y because this is more than 88, and it can't be rubidium because it's too small, 84. And based on that, we can find from the periodic table that the average atomic mass will be 87.6. Then, let's look at the third question. How many protons and neutrons are there on the isotope of the element with a mass number of 88? Since we know that this is already strontium, so this is going to be strontium 88. And we know that the atomic number of strontium is 38. So to find the protons is equal to 38. Okay, so sorry, this must be 38. And then the number of neutrons is we subtract 88 minus 38, and that brings us to 50 neutrons. There you go. Now, let's look at another question. So we're asked here to find the average atomic mass of copper. So that is 1. So we like to find the average atomic mass of copper based on this. And how many protons and electrons for the 65 isotope. And this is interesting, using 10 copies of atom, we draw a particulate view. So we will get there. Let's see. First, based on this mass spectrum of a pure element, represent what is the average atomic mass for this? So basically what we do, we got here copper, we have got here copper 63 and copper 65. And then we see that this is going to be 30% for the 65 and around 70% for copper. And this is multiplied by 63, multiplied by 65. That's our atomic mass. And I think we have this already before. Yeah, I think we have this already. Let's just go back. There we go. So we multiply that, we got 44 and 20. There you go. So this is going to be equal to 44, and this is 20, and that equals 64 AMU. Of course, this is an estimate. Now, how many protons and neutrons are at the mass number 65? So we have here copper 65, and in the periodic table, copper has 29, atomic number 29. So the number of protons is 29, and the number of neutrons is 65 minus 29, which will give us 36 neutrons, and these are your protons. Now, here's the thing. Using 10 atoms of copper, draw a particulate view showing the relative abundance of each isotope. Okay, now we don't really need to kind of, you can just write this randomly. Let us represent the one with the shaded, the blue one, as your copper 63, and the copper is, copper 65. Remember that copper 63 is more abundant, 70%, and 30%. So what is 70% of 10? That will be 7 over 10, and 30% of 10 is 3. And therefore, we can write it this way, that there is 7 of the copper. There is 7 of the copper 63 and 3 of the copper 65 out of the 10. So this is how you're going to draw the particulate view. Now, sometimes, like in this kind, mass spectrum of element X. So again, we will look at it, and you would notice that this one is X7, and this one is X6. And if you look at the intensity, this is 100, as you can see, and this is 20. It does not add up to 100. So what you do is like this. We write the X6, and we write the estimated atomic mass. We'll look at the relative abundance. You see 20 over 120, because this is 20, this is 100. They don't add up to 100, so we get the percentage, or at least the fraction. 20 over 100, 1 over 120, and that's when you multiply. And we get 6.8. And the closest to 6.8 will be lithium. Okay? So these are some of the most common questions that comes out in AP. So I hope that helped. And if you have any questions, feel free to consult Mr. Garcia. Thank you.